Welcome back. In the last class, we have seen our different methods for controlling our DAV. We have seen single phase shift, extended phase shift and dual phase shift, and we have understood what is the importance of degrees of freedom when we want to have a greater degree of freedom and why those degrees of freedoms are important for us. Then we have started our discussion on AC to DC converters. So they will be used at two different locations. One will be on the charger side, they will be the front end component or the first component which will be seeing after the grid. Then we have also seen that they will be placed inside your electric vehicle, where after the DC to DC converter we will be having a DC to AC converter which will be connected to your electric motor. Then we have discussed the diode bridge rectifier and what happens when we have an capacitor or an battery bank at the output stage. We have seen that the current becomes peaky when we have an constant voltage at the output side. So, to address those issue of your peaky current or to improve the current profile which is drawn from the AC source, we have started our discussion on boost power factor correction circuit. So, here we are using the boost converter, boost DC to DC converter to rectify our power factor. Okay. So, in this circuit we have also seen the working. So, when the switch will be closed, so it will be subjected to mode of Vs because the diode bridge will be rectifying our AC supply. Mode of Vs will be applied across this inductor L when the switch is on. When it becomes off or when we remove the gate pulse from the S1, it discharges and it experiences a voltage which will be equal to mode Vs minus Vo. Okay. So, we have also derived this duty ratio. We have also understood that the duty ratio will be variable now because our Vs is variable, it is an AC signal. So, its magnitude will be changing with respect to time. So, the rate of charging will be dependent on the duration of the cycle. Okay. So, at the near the zero crossing, the charging time will be higher or the duty ratio will be maximum, or the switch has to be turned on for more number of time because the charging rate is less. So, it will take higher time to reach the required current. Then at the peak value the voltage will be higher. So, the duty ratio will be less. That is what can be seen from this function 1 minus mode Vs by Vo. So, we have seen this graph also. So, in this case this is the duty ratio where it is nearly 1 at the zero crossing. Okay. So, and there will be a nearly 0 duty ratio at the peak values. Okay. So, why? Because the rate of charging will be higher in this case. So, we can turn on the switch for a smaller time and we will reach the required current level. Then we have started our discussion on our inductor sizing. Okay. So, what will be the voltage across the inductor when the switch is on? For how much time the switch will be on? It will be on for d into t into Ts. Okay. So, now we have replaced the d with d of t because it is a time variable function now. So, d of t into Ts, it will be equal to L into delta I. Okay. So, now this Vs will be the voltage which is applied across the inductor. That is what we have written, assuming the same, that our switching frequency is very high than the supply frequency. Then rearranging the equation, we will find out that our d into t into Ts will be equal to L delta I by mode of Vs into t. Okay. Now, during 1 minus d Ts time, that is when the switch is off, what will happen? Now, inductor will be experiencing a voltage which is equal to the difference between the input and output voltage, that is rectified source voltage minus of Vo will be equal to minus L delta I by 1 minus d into Ts. Okay. So, again simplifying that, finding out it terms of our turn off time. So, this will be my change in current value divided by the voltage. Then after adding 1 and 2, that will be giving me the entire switching time period, that is d of t into Ts plus 1 minus d of t into Ts. When I add them, it will become equal to Ts. So, this will be the value of Ts in terms of my delta IL divided by the voltage parameters. Okay. So, when I rearrange it, I will find it out that delta IL will be given by this function where it will be equal to mode of Vs into in output voltage minus mode of input voltage by L V naught into switching frequency. Okay. So, in this expression, if I differentiate it, because it is having a sinusoidal term, so it is also a variable. So, how I will design the inductor? I have to find out where there will be a maximum change in the inductor current. So, to find the maximum value of this equation, I have to differentiate it and equate it to 0 to find out the maximum point. So, where I will see that after differentiating that the maximum point will be located at B0 by 2 or when my input voltage is equal to 50% of the output voltage, at that point I will see that the inductor will be having a maximum variation in its current. Substituting this relation which we have just now obtained in question 3, we will find that my inductor size will now be given as V0 by 4 into delta IL max, that is the maximum value into the switching frequency. Okay. Now, the capacitor size. Okay. So, how we will design the capacitor? Now, we have already decided what will be the inductor size in the last slide. So, here we will be determining what will be the capacitor size. For that, we will go for this relation. Input power is equal to output power, neglecting the losses. So, P in will be equal to Vs into sin omega t. This is my input voltage, this is my input current, assuming that the Boost PFC is operating and it is maintaining the unity power factor. So, we have not considered any cos phi term over here. So, we have perfect unity power factor. So, the phase shift between the voltage and current is 0 over here. So, my current will be Is into sin omega t. So, when I multiply them, I will be able to find out the input power. Okay. Now, if using the trigonometric equations and simplifying it, I will find out that it will have two terms. One will be the constant term, one will be having an double frequency component, that is Vs Is cos 2 omega t by 2. Okay. So, the same equation has been rearranged or simplified. Now, output power. Okay. So, what will be the output power? Output power will be equal to V0 into Id into T. Okay. So, why this is equal to Id of T? If I apply KCL at this node, we know in steady state the capacitor will not consume any amount of current. The moment it consumes some current, net current, so its voltage will be changing. Okay. So, it will not consume any current. So, whichever current is coming through the diode, it is obviously it will be equal to the load current. Okay. So, my load voltage is V0, okay, assuming the capacitor is sufficiently large to support, or we can neglect the delta V naught. So, V0 will be V0 into I dt will be the output power. So, here we have the input power, here we have the output power. Now, equating both of them and solving, I will find that Id V0 into Id of t will be equal to Vs by 2 minus of Vs cos 2 omega by 2, okay, where Id is equal to I load plus Ic. Okay. So, this load is drawing an constant power because we have an resistive load and we are assuming or neglecting the delta V naught or the ripple at the output voltage. So, this constant term will be representing the power which is consumed by the load. So, we will handle this ripple content. So, this will be absorbed by my capacitor, or the capacitor has to be designed in such a way that it will be able to absorb this ripple content besides maintaining the voltage ripple within the given percentage. Okay. So, now here Ic of t will be equal to minus Vs Is cos 2 omega by 2 V naught. Okay. So, this we have now determined the current. So, based on that I know that what will be the ripple percentage if I am subjecting any amount of current through a capacitor, it is given as 1 by C integration of the current through it. Okay. So, if I integrate the expression which we have just calculated and replacing these terms Vs Is by 2 as IL, I will find that it will be equal to I load by C minus of cos 2 omega t, okay, into dt. Upon integration it will be the result. Now, cos integration it will be minus sign. So, we will get this as our expression I load by 2 C by omega, because we had 2 omega. So, that will be coming outside and divided with the denominator. So, we will get V ripple as this function I load by 2 C omega into sin 2 omega t. Okay. So, now voltage ripple peak will be equal to I load by 2 C omega, that is the peak value of this value. Okay. Like the same operation we have done for our inductor. After we have found out the delta L value, we have differentiated it to find the maximum value of that. Here the equation is pretty simple. We know the maximum value of this sin 2 omega t will be 1. So, the maximum value of delta V will be when this sin is omega 2 omega t is equal to 1. So, sin of 2 omega t is replaced as 1. So, we have got the peak ripple as I load by 2 C omega. Okay. So, now what is our observation in this case? What will be the capacitor size? This is the peak to peak ripple which we have obtained. So, now if I rearrange that, I will see that it will be equal to I load by omega into delta V naught. Okay. So, here this V ripple is nothing but the ripple from 0 to the average value to the peak value. Okay. So, 2 into V ripple will be my peak to peak ripple or delta V naught. So, that is what has been replaced over here. So, now I load, I will be multiplying it with the numerator and the denominator with the term V. So, I will can replace this I load by P load divided by V. So, this will be the expression. So, here this final expression can be used to design your capacitor for our Boost PFC design. Okay. So, here we have seen the design of inductor, we have seen the design of capacitor. So, now what is the merits and demerits of this circuit? Here if you see this capacitor, it is subjected to 2 omega term, okay, twice of our line frequency. Okay, so not this is not your switching frequency, whereas when if you remember the calculations which we have done for a boost converter, there the capacitor was function of switching frequency, whereas it is the function of 2 times of line frequency or 100 hertz component, assuming the supply is at 50 hertz. So, the capacitor has now designed to absorb 100 hertz component. Okay. So, because of that your capacitor size will be very high compared to an DC to DC converter which were designed for handling your switching frequencies. Okay. So, this brings one of the major limitation of your boost PFC operation, that large size of your capacitor will be required because it has to handle 2 times of line frequency. Okay. Advantages of this circuit. So, now compared to our diode bridge rectifier which was connected to an battery bank or an capacitor at the output stage, we have seen that the current was peaky, whereas in this case we have seen that we are almost able to make the current sinusoidal. So, there are no peaky currents which are drawn. So, the device rating can be reduced compared to the previous case. Demerits: higher component count because we have introduced one DC to DC converter in addition to the components which were present in our previous solution, that was only diode bridge rectifier. So, the component count is higher, so footprint will be higher or the cost will be higher compared to the previous solutions. Okay. So, in this case 3 switches are in conduction leading to loss. Okay. So, what is the meaning of that? In any state, whether the switch is on or off, whether we are in the positive half or in the negative half of the cycle, we observe that 2 diodes will be in the conduction path. Suppose we are in the positive half, so these 2 diodes will be in the conduction path, and when the switch is on, so 2 diodes and 1 switch will be conducting. When S1 is off, 2 diodes and the output diode will be conducting. So, always 3 devices are in the conduction path, 2 diodes plus 1 switch or 3 diodes. Okay. So, when the current flows to these devices, although in our analysis till now we are not considering the on state drop, so they will always have some type of on state losses. So, because of as 3 devices are in the path, the losses will be higher compared to the previous solution where we had only 2 diodes in the path. Larger capacitor size, we have just now calculated and seen that it will be forced to absorb 2 times line frequency component. So, its size will be increasing. Okay. So, more higher is the frequency, less will be the size of capacitor. Here we are subjecting it to 2 times of your supply frequency rather than the switching frequency, which is very high. Here 2 times supply frequency will be at 100 hertz or 120 hertz based on 50 or 60 hertz supply. So, the capacitor size will be bulkier in this case, or the capacitor will have an greater footprint in this converter. So, till now we were discussing in the CCM mode of operation where the inductor current was continuous. Okay. So, we can have the complementary operation of your boost PFC, that is in the DCM mode, discontinuous conduction mode, where inductor current will be discontinuous in this case. Okay. So, can we still maintain our requirement that we wanted almost unity power factor over here, or the input current which were drawn should be sinusoidal? Okay. So, we will check that through analysis. Okay. So, now as my current is discontinuous or I am in the DCM mode, so the current will be 0 for finite duration. That is what we have assumed, that switch is conducting for Ts 1 time and it is discharging to the diode for Ts 2 time. Okay. The total sampling time is Ts. Okay. Now, BL will be equal to L DIL by dt. So, for the turn on time, when the switch is on, again we will have this mode Vs which will be applied across the inductor. Mode Vs will be equal to L delta L peak by Ts1. Okay. Ts1 is this duration for which my switch is on. Okay. When the rearranging that, okay, so it will be equal to IL mode of Vs into Ts1 by L. Okay. So, now IL peak has become a function of rectified sine wave. Okay. So, if you see what is our observation in this case, the peak value of current is function of the mode of input voltage or rectified sine wave. Okay, so this mode of Vs is nothing but the rectified sine wave. Okay, if IL is function or proportional to your mode Vs, what can be my conclusion? At this point, what will happen? I have unfolding, or I will be, because of the diode bridge, the rectified sine wave will be reflected as a full sine wave over here, okay, because of the switching operation or the flip of your diode operations in the positive and negative half cycle. So, Is will now become proportional to Vs, okay, or I can have sinusoidal current drawn from the source even if I go into the DCM mode of operation. Okay. So, let us continue with the analysis. Now, what will be the area under this curve? Area under this curve will be equal to, now we have found out the value of peak. Okay. Why this is in place of delta L, we have replaced it with the peak value, because always the starting point is 0 in this case, because we are assuming DCM mode of operation. So, the current will start from 0 everywhere. So, delta L can be replaced by your IL peak. Now, the area under this shaded region will be equal to, we can split it into two triangles where the height is IL peak and the base is TS1 and TS2. So, that will be half into, this is the height of the triangle or the peak value of current which we have denoted. Now it will be equal to multiplied with TS1 into TS2. Okay. So, half into the area height of the triangle and the base of the two triangles. Okay. So, we are just calculating this area by splitting it into two triangles, that is what we can assume. Then the average value of this one, IL average, will be equal to half into this triangular area, okay, divided by the time period. Okay. So, we have found out the area. Now, we are finding out the average inductor current over a cycle. Okay. So, divided by Ts will be giving me the average inductor current value. D1, what is D1? It is the time for which the switch was on. What is D2? It is the discharging time of my inductor or the turn off time. So, I have removed the pulse from here till the current through the inductor becomes 0. Okay. So, that is what is defined as D2. So, it will be now equal to D1 Ts into D1 plus D2. Okay. So, the equation, the same equation has been written over here just by replacing the Ts1 Ts2 by the respective duty ratios. Okay. So, now applying the volt second balance, that is during the on time the inductor was subjected to mode of Vs into D1 into Ts plus the difference between mode of input voltage minus output voltage, that is the difference between input and output voltage for the time for which the inductor was discharging, that was D2 into Ts. Okay. So, that has been equated to 0. I will find out that D2 will be given by this expression. Okay. Now, substituting this D2 in value of D2 as in terms of D1 in equation 1, we will observe that average inductor current will be given by this value. Okay. So, what is our observation in this case? If I see, the average inductor current is also a function of sine wave. Okay. So, in whether I am in the CCM mode or in DCM mode, I can ensure that this current which is drawn is not peak in nature, it is following our required sine curve. Okay. So, now in this case, if I plot the source current, what will be the current profile over here? Okay. Here we have seen that it is proportional to Vs, mode of Vs. Okay. So, whenever we see it after the rectifier, it is mode of Vs, which is the source over here. Okay. So, here in this case, what will be the Is current? Small gaps in between, because we are in the DCM mode of operation. So, this is the charging and discharging, and it will be an function of your sine wave. Okay. So, if I observe the current which will be drawn from the source by using an Boost PFC in the DCM mode, it will be having almost sinusoidal shape, okay, charging and discharging and so on. So, this will be the current which will be drawn from the source. If I see the envelope or the peak value of this current, that is what we have derived. The peak value of my inductor current will be proportional to sine wave. Okay. So, that is why we have got an sinusoidal average current drawn from the source, even if my Boost PFC is operated in DCM mode. Okay. So, based on my application and my requirement, I can design the Boost PFC to operate in CCM or in DCM mode. Okay. So, we are not going into the designing of inductor and capacitor in the DCM mode. Okay. So, now till this what we have seen, we have discussed our Boost PFC in CCM and DCM mode. We have identified its advantage and demerits. So, when I say in terms of advantages, the current is no longer peaky, the power factor is maintained nearly unity compared to our previous solution. Demerits, here we have seen that 3 devices will be in the conduction path always. Okay. So, whether the switch is on, when the switch is on, 2 diodes and 1 switch was coming in the path. When the switch was off, 3 diodes were conducting. Okay. So, 3 device onset losses will be encountered, or they will be responsible for your loss in this circuit. Okay. So, if I have less number of devices in the path, the losses will be less. So, can we have some solution where we can have lower number of devices in the conduction path? Yes. So, the one of the other solution is your bridgeless PFC. Okay. So, in this solution what will be done? Now, we will try to combine this diode bridge rectifier with the boost converter. Okay. And try to design a solution which will require minimum number of components, and it will have better efficiency compared to our Boost PFC, where the number of devices in the path for any given time period will be less than 3. Okay. So, here this is the circuit diagram of bridgeless PFC. What changes has been done over here? The inductor has been moved from the DC side of the circuit. Okay. So, if you see, we had mod Vs over here. So, it was subjected to DC component. Okay. So, whereas in this case it has been brought to the AC side. So, it will be subjected to bidirectional flux now. So, when we have such, when I compare the inductor size in both the cases, I will observe that when it is connected on the AC side, I will have reduced inductor size requirement. Okay. So, the size of inductor which is used on the AC side compared with the DC side, in the DC side we will require a bigger inductor, whereas on this solution where we have moved it to the AC terminals, it will require less size of your inductor, or its value requirement will be less. Okay. 2 switches of this rectifier are replaced by active devices. Okay. So, there we had 2 diodes over here. These 2 lower diodes has been replaced by 2 switching devices, may it be MOSFET or IGBT as per the power rating of the converter which is designed. Then we are removing the other components. Okay. So, what is the circuit now? We have an inductor on the AC side, we have 2 diodes and 2 switching devices with antiparallel diodes. Okay. And we have an capacitor at the output stage, and R is your load resistance. Okay. So, here this switch can be MOSFET or IGBT, any fully controlled devices can be used over here to realize this to switch S1 and S2 as per the power rating. Now, what will be the operation of this converter when the switch is on? Okay. So, when in the positive half cycle, I will turn on this S1. Okay. So, we will get 2 equivalent circuits for each half cycle. We are now going for the positive half cycle. In this, the AC voltage will be positive, and now I have turned on S1. Okay. So, what will happen to the current? The path is shown over here. The inductor is now charging. If you apply KVL in this loop, I will see that there is no other opposition in the path, neglecting the onset drop of the device. The inductor will be connected in parallel with your supply. So, the inductor voltage will be equal to supply voltage when my switch 1 is on. Okay. Now, so obviously in this case, as the inductor is connected across the supply, it will experience increment in its current. After the current has been charged, I will remove the gate pulse for the remaining part of the cycle. For 1 minus d into Ts, the pulse through S1 is removed. Now, we know the behavior of inductor, it was carrying current in this direction. So, it will try to maintain the current in that direction, and it will flow through. Okay. So, here inductor has forced the current through diode D1 and the antiparallel diode across the switch 2. Okay. So, now this will be the path and the inductor will be discharged. Then after I will come back to my switch on time, again in the next after DT time I will go back to the switch off case, then this will be repeated. Okay. So, this is true for positive half cycle. Now, what will happen in the negative half cycle? My voltage polarity will reverse now, as we have AC in the input side. In the negative half cycle, the voltage polarity will be reversed. So, in this case, if you see, we are turning on S2. Okay. So, when I turn on S2 or give gate pulse to S2, what will be the equivalent circuit? The current will be flowing through this path, okay, in the directions of arrow. Now, if you see, the inductor is again connected across the supply. So, it will experience increment in the current, but in the opposite direction. If you mark the direction of inductor current, it was in this way. In this case, in the negative half cycle, it is subjected to the opposite direction of current. Okay. So, this is the main reason why the inductor size is less over here compared to your Boost PFC, because there it was subjected to unidirectional current because it was after the rectifier stage. Here it is subjected to bidirectional current. Okay. So, your core will be better utilized, or the size of your inductor will be less over here. Then when after the charging is done, I will remove the gate pulse. We know the behavior of inductor, it was carrying current in this way. So, it will try to circulate the current in the direction, and the path is shown over here. Okay. So, it will flow through this, then the diode, then to the output stage and back to your inductor for the supply. Okay. So, here the inductor is discharging for 1 minus dTs time duration. Okay. So, this is the operation of this converter. Okay. So, where we have seen that during the positive half cycle, I will turn on S1, during the negative half cycle I will turn on S2 for dt time, then I will allow it to discharge the diodes after my inductor has been charged. Now, advantages of this circuit. So, obviously the inductor size is less over here because it has been shifted to the AC side terminals. Now, the conduction loss is less. Why it is less? Let us go for an approximate calculation. Okay. So, here if you see how many devices are there in any stage. If you see in this case, how many devices are coming in path? Here we have switch 1 and the diode across this. Okay, 2 devices. So, over here when the switch was off, in the next iteration, these 2 diodes are in the path. In this case, the diode through this and the switch. Okay, here again 2 diodes which are in the path. Okay. So, everywhere for all the switching combination, all the 4 switching states, I see that only 2 devices are coming in the path, whereas in the previous case 3 devices were in the path. So, I can say that the conduction loss over here will be less compared to the previous solution. Current through the inductor is bidirectional. Okay. So, this will be giving us better utilization of inductor core. So, the size can be reduced. Now, lower component count. Over here the component count, if I see the Boost PFC, so where we had diode bridge rectified followed by the boost converter stage. So, the component count was higher. In this case the component count is less. So, the circuit will be cheaper to design. Duty ratio, d minute wise the duty ratio is variable over here. Okay. So, again if we go for the analysis, we will see that the turn on time period for which the switch 1 or 2 was operated, they will be function of the supply voltage, or they will be function of sinusoidal quantities. Okay. So, they will be having different rates of charging. So, because of that the duty ratio will be variable in this case also. The diodes operated in the switching frequency. Okay. So, what is the meaning of this statement? If you see the 4 equivalent circuits, the diodes, what will be the frequency of current which is flows through the diodes in this, in the all the 4 combinations. If you see the diodes, here your switch was conducting, after I have removed the pulse, the diode 1 has come into path. Okay. So, this will be repeated every switching time period in the positive half cycle. Okay. So, every time or at every switching instant, diode will be turning on and off. Okay. So, this diode D1 is operated at switching frequency. In this case if I observe, same thing will be happening with the D2. It is operated at switching frequency. Okay. So, that is why it was written that the diodes are operated at switching frequency. Okay. So, when I consider the switching losses of the component, the switching loss of a diode will be much higher than the MOSFETs or IGBTs. Okay. So, because of this, as the diode is operated at switching frequency, the switching losses will be higher over here. The conduction loss will be less because 3 devices, instead of 3 devices, now we have reduced it to 2. But at the cost of increased switching frequency. Why? The diodes, if you remember the operation of your diode bridge rectifier, they were operated at 50 hertz. In the positive half, D1 and D4 were conducting, in the negative half, D2 and D3 were conducting, and they were operated at line frequency, whereas in this case they are operated at switching frequency. Because of that, they will be creating higher amount of switching loss. What is then solution for that? Okay. So, the other solution for that is totem pole PFC. Okay. So, in this totem pole PFC, now the position of the switches has been changed. Here we had the switches on the lower side of the both the legs, whereas in this case we construct one leg with the switches, one leg with the diodes D1 and D2. Okay. So, one leg with the switch and one leg with the diode, and we will see the operation that one of the leg will be operated at high frequency, which is having the switching device, whereas the diode leg will be operated at low frequency. Construction of this one, So, if you see the device count, everything is same, just the arrangement has been changed compared to your bridgeless PFC. The active switches are now moved on one leg, so that will be operated at high frequency, the other leg will be operated at line frequency. Okay, so we will see that. The passive switches or the diodes are moved into the another leg, which will be operated at low frequency. This switch can be MOSFET or IGBT as per the power rating of the application. Now, what will be the operation of this converter? In the positive half cycle, I will turn on S2 switch. So, the current will be flowing in as shown in the dotted line. Okay. So, it will be flowing through this. What will the voltage across the inductor? Again, it is experiencing the source voltage. Now, when I remove the gate pulse from S2, I will turn on S1. Okay. It will flow through the switch 1 and this will be the path. Okay. Now, if I see the inductor is discharging. In the negative half cycle, if you see, I will have for charging, I will be turning on S1. So, it will be flowing through this path, and for discharging I will turn on S2. Okay. So, if you see over here, the switches are operated at high frequency and the diodes are subjected to the same amount of current when they are discharging. Okay. The advantages of this totem pole operation, the inductor size is small, conduction losses is less in this case. Why? Because again we have two devices in the conduction path. Current through inductor is bidirectional, so the size of your inductor will be less. The diode is operated at line frequency, leading to lower losses. Okay. The switching frequency operation of the diode is avoided in the totem pole compared to the bridgeless PFC. In bridgeless PFC, they were operated at switching frequency. Now, the diodes will be operated at line frequency. This disadvantage of this circuit, the duty ratio is still variable. They will again, I want the current to be sinusoidal over here. So, the duty ratio will be variable. Okay. Not suitable for low power applications. Okay. So, till now what we have seen, we have come across your Boost PFC operation in the CCM and DCM mode. Then we have seen our Boost PFC, then in the DCM mode of the Boost PFC, then we have gone into our Bridgeless PFC, then we have seen the Totem pole PFC. We will continue with this discussion in the next class. Thank you.